What can undershoot do? Undershoot will result in double clocking. Overshoot can burn the chip. When do you consider a piece of wire is a transmission line? It's a common rule of thumb. When the physical length of the circuit is greater than 1/10 of the wavelength, then we can consider the wire as a transmission line. When a conductor becomes physically long compared with the wavelength, there's a phase shift as they travel along the line. They were aligned at point A. Now, let's say the point A has moved on the voltage and the current. Let's say this red one is current. The point A is not the same, it's not in phase anymore. There's a significant phase shift. The wave undergoes, the waves undergoes a significant phase shift. Any question on this?
So then what happens when there's a phase shift, sir?
Okay, so when there's a phase shift, very good question, which I'm going to talk about next. When there's a phase shift, since you asked this question, let me address now. So when there's no phase shift, right, the voltage, this is a voltage, and then the current, they are in phase, right?
Yes, sir.
So when there's a phase shift, so when they're in phase, then the voltage divided by current will have a constant impedance. Okay.
Okay,
so
sir.
when the phase is not when there's a significant amount of phase shift, what happens is the characteristics impedance changes. Okay.
Okay, sir.
So I will give you a few examples. Let me back up, go to electromagnetics and look at our basic lumped element circuit. Then from there you will get further explanation. Anybody? Any other questions?
No, sir.
Okay, let's back up and go to the electromagnetic theory. You know, in electromagnetic, do you remember a transmission line can be represented by an inductance, a resistor, R, L, R. Okay, in this case, if the length of the circuit, if this length of this circuit is very much smaller than the wavelength, and then we call this a lumped element model. It's called the lumped element model. You guys remember this from your electromagnetics class? This is conductance G, and this is C. This is a model, lumped element model of a transmission line of a conductor. We just take a small section of the conductor that is very much smaller than the transmission line. Do you remember what is the L stands for? It's inductance of the wire, right?
Yes,
It
sir.
can be any inductance. Every wire that's carrying current will have a magnetic field around it, right? And also there can be lead inductance or any other inductance. All this is lumped in this L. And the R stands for resistance. It has a wire, then definitely there's going to be resistance. As we mentioned earlier, at higher frequency, we're going to have skin effect also. Everything is included there. Can anyone tell me why what is this C? What is this C representing?
Capacitance.
It's capacitance. It's a modeling something in the conductor. So which part of the conductor is it modeling?
Sir.
Let's say if you go for the interview and then the guy said, asking you this question, you draw a transmission line model, then you're drawing it, then he's asking you, what does the G do? Which part of the conductor physically is modeled by the G? Okay, now I'm just drawing a regular conductor, call this outer shield. Such LD. Usually the shield is metallic, right? Shield provides a return. So like this part of the thing is the outer shield. In the transmission line model, the return outer shield. So then you have a center pin, right, that carries the current. You have a center pin that where the RF current enters, and this is the representing the center pin. This part here.
Understood, sir.
Okay, so the current enters here. This is like a center pin. Very good, you understood. See, our job here is to make you guys learn something. And we are here, we want to make sure that when you go for an interview, when they ask you a question, you answer it, and you're going to get a job. Right?
Yes, sir. Correct, sir. Yes, sir.
So let's say if you have a load here, for example, if you put a load here, see in this class, I'm not going to be teaching very difficult things. We are only teaching the fundamentals that will allow you to do your own exploration in the future. You can go to graduate school with these fundamentals, or you can go and get a job in this area and further enlighten yourself with practical knowledge. So center pin, let me put this in color. Center pin, outer shield. We usually used to talk in, currents go through the load and then returns, right? Then we have a generator here. Usually the generator will have a source impedance. We call this is GS. Later on, we will look into this in detail. And then we have a VG, the generator, voltage of the generator. So complete. Hello?
Yes, sir.
Can see?
I can see, sir.
I don't know why it's keep disconnecting.
It's okay, sir.
So, okay. All right, sir. If you look, sir, at this here is the insulator, right? Insulator. Then you will have maybe I'll draw the pin in a different color. So this pin is protruding out. You have a center pin. Okay, if I draw the cross-sectional view, cross-sectional drawing. And the center is the pin, let's say. This is the pin, and then this is the outer shield. And this is the pin in the middle. And then you will have this insulator. Okay, so what Zakian said is very close to. So there's always some kind of leakage from the insulator, from the pin. There's always some small current leaking from the pin to the shield, because there's a voltage difference, isn't it?
Yes, sir.
Okay, so that current leakage is represented by this G, conductance, and G is 1/R. Okay. So you know that in the center pin is at a different potential, and the outer shield is at a different potential. So there is a potential difference. There are moving charges of different potential. Therefore, we're going to have some capacitance also. And this is the capacitance that is shown here. So this is what we are doing in this case. We are just taking a small section. We're just taking a very small section here. We can call this delta X, a small section, which is very much smaller than the wavelength. And that's what we call the lumped element model. So any question?
No, sir.
No, sir. Understood,
Sir,
sir.
can you hear me?
Yes.
Want to ask, what's the difference between a lossy transmission line and a normal transmission line?
A very good question. Who asked this question?
The Zagian guy you
sir.
mentioned.
Zigzag Yan. Okay. Very good question. So now what you see is lossy. What causes the loss in a wire? The only thing, let's say you have a piece of wire, right? You have wire with a resistor and a current going through I and a resistance R. So the loss is caused by I squared R, right? right or not?
Yes, sir.
So the loss is caused by all the resistive element or the conductance, resistor or conductance, because conductance is also is a function of resistance. So if you remove G and R, then it becomes a lossless model. So right now what you see is a lossless model. This is lossless. So this is lossless. Sorry, this is lossy because we have the resistance and the conductance, lossy. For the lossless model, okay, let me just copy this out. Lossless model. Lossless model, you just remove the resistor. What I mean by remove means you just short the resistor. Okay, you cannot remove the resistor or open the resistor, because if you open the resistor, signal cannot go through, right? Okay,
Right,
so
sir.
yeah, so we assume this wire doesn't have any skin losses or any other losses. So we short out the resistor and it becomes lossless partly. Now you come to the G. Of course, the G has to be removed. You cannot short it. Once if you short it, that means you are shorting the output. There's no output. Okay, you are shorting the output signal to ground. So you cannot remove the G this way. You just open circuit the G. And this is the lossless model. Did I answer your question, Zach?
Sorry, sir. I was halfway disconnected. So what I understand is that the difference between lossless and lossy is lossless has the dielectric conductance consists in the model itself.
For
Correct?
lossless, you don't have the resistor. Okay, I short this resistor out.
Okay.
Okay, anybody disconnected, you can ask me to explain again. You just short resistor. Okay, then you also remove this open circuit, short circuit, open circuit. So that will make this lossless. See, now it only depends, there's no resistor or conductance that can dissipate the energy as heat. Correct? You only have
Yes.
storage elements, inductor and capacitor. Assuming, as I said earlier, this is a lumped element model. We're assuming this is ideal inductor, ideal capacitor. There's no lossy elements inside here. For now, just assume this is ideal L and C. So this is a lossless model. Any other questions? Still anyone not sure about this? Is everybody still connected?
Yes, sir. Still here, sir.
Connected.
Yes, sir.
If anybody got disconnected, you can always tell me, then we can stop it and start. Okay, what happens for a long transmission line? For for long transmission line where L circuit length is very much bigger than the wavelength, you will get the distributed model. You will get the distributed model. In this case, the physical size of the element is comparable to the wavelength. The same thing that you drew earlier, lossless. I'm using lossless here. Lossless means there's no conductance, there's no resistance. So this is for a long transmission line. Long transmission line. So in this line, so these are called distributed inductances. Distributed inductance. So this is a distributed element model. A distributed element model will have, for the case where the length of the circuit is much bigger than the wavelength, then we have a distributed model. We just put the lumped element model in series and form them into a long conductor. Okay, distributed. So these are also distributed elements. Distributed capacitance. Say if you have a signal coming in, digital or analog or whatever, just draw a digital signal. Nowadays, all digital signal that you're going to see are going to be at RF frequency. We are not going to transfer, like, you go anywhere. Now you go to a machine to draw money and you don't want to wait there for 5 minutes. The signals has to travel very fast. Accept your card, do verification, and then process how much you want, and then activate some device to distribute the money to you. Then after taking it, it will sense that you've taken the money. So all this must happen very fast. Usually signals, I don't know, people have many ways to represent how signals propagate. Some say they propagate like this: charge, discharge, charge. Once discharging here, it's charging here, and then discharging here. So this is a propagation of wave. This is one way of drawing it. Call this ideal case, ideal. Non-ideal case is the high frequency circuit. In this case, a wavelength is very much bigger than the circuit length. In this case, the length of the circuit is very much bigger than the wavelength, or comparable. Or approximately one or the other. In ideal case, we think that as soon as a signal is transmitted, and you have a transmission line usually represented by 2 wires. In ideal case, as soon as signal transmitted, it will be received. As soon as say that you are transmitting a signal and then it's received on the other side, no problem. This is the ideal case. For non-ideal case, there's a propagation delay. We look at a pair of wire as a transmission line. The one way of drawing a transmission line, you can draw a transmission line like this. The center conductor. This is indicating you have a center pin and outer shield, or you can draw it in this way. This is the transmission line part, you know, TL. So like, you know, current going through a load and then returning to the source. So there's another way you can draw the transmission line. So in non-ideal case, when you send a signal, the wavelength is much shorter than the length of the circuit. You have a load here, let's say. In non-ideal case, there is a propagation delay. Delay that is finite and measurable. Measurable. How do you? Measurable. That's measurable. You might be telling, you know, okay, the thing is traveling at a speed of light. What's the big deal? A delay. You might say that, right? Am I right? Am I right, Bibi?
Yes, sir.
What's the big deal about the delay? Because things are traveling at the speed of light. But you know, you must understand, we're just not talking about one piece of conductor here. Sometimes the line length can be very long, or even in the circuit board itself, you have so many traces. It is so small, the chip, but the length of the trace, it can be a few kilometers. Maybe I'm exaggerating. It can be quite long. Signal has to travel back and forth, so there's going to be delay. But we are just representing all these things with one piece of wire. So what about, are there any questions so far?
No, sir.
No, sir.
No, sir.
So, okay, again, we already went through, I'm just summarizing this quickly as possible. You know, in ideal case also, we assume that when you send a pulse, and then on the other side, you receive it nice and clean, right? In the ideal case. You send a pulse, ideal conductor, no losses. No losses. Sent, arrive at load. Okay, no problem. No distortion, no ringing, and no ISI. But in a non-ideal case, they are parasitics. That react resulting in attenuation or ringing. Ringing due to impedance mismatch. Okay, these are the parasitics we are talking about. These are the parasitics. Distributed inductance and capacitances. So when the line is long and the signal has to travel, and if there's a mismatch along the way, I will tell you what the mismatch is, then you'll end up getting something like this. Ringing. Sometimes signal also can attenuate, you know. Signal can die and you end up getting nothing on the other side. Okay, another thing is, in ideal case, again, we assume there's no reflection. Ideal case free from any reflection. Reflection, interferences, is on the conductor. Interferences on the conductor. So again, you know, whatever you send, whatever you're sending, it's going to be receiving pretty good on the other side. Send, receive. But in actual case, any signal encounters a change in impedance. In actual case, any signal encounters a change change in impedance. Okay, instead of talking about it, let's do a quick. Let's say you have a signal traveling, talking about a transmission line here, and then you have signal traveling. Then you have a VR. You know what's a VR, right? Last time you guys have studied VR. So you have 50 ohms here. Okay, let's say you have 50 ohms in the transmission line. But when the signal go into this VR, it's going into the VR. But then at the VR, it's not 50 ohms anymore. So you're going to get a reflection. That happens in actual case. Transmission line effect. Another thing that can happen is again 50 ohms. Then you come here and then you encounter a load that is not 50 ohms. There's a mismatch, and then there's going to be reflection again. For reflection, I just put a reflection coefficient, gamma or something. So there's going to be reflection. So when it reflects, if a wave get reflects, and then there's another wave going into the forward, the other signal going backwards, they're going to interfere, causes interferences. Standing wave. Standing waves and other effects. Are you guys okay?
Sir, one question.
Yes.
Why does let's say when we include a resistive load in the model, it will cause reflections, but when we includes capacity loads, it causes a different types of. Is it like that? I'm not sure.
You're saying that when you have a transmission line,
Yes.
right? You have a 50 ohms, and then you put a load here.
It will,
When you put a
it will cause reflection.
Or when you put a capacitor, so let's say you are doing this at a particular frequency. At what frequency? Just assume your frequency is 2.4 gigahertz or something. Okay. If you put a capacitor there, then this is going to be 1 over j omega c, right? Let's say you have a frequency, let's say omega is 5 gig radians per second. Then if you go and put a capacitor there, depending on the value of the capacitor, this is going to make the capacitor load a low impedance load. Low impedance because 1 over j 5 times 10 to the power of 9. So your capacitor is 1 nanofarad, assuming 1 nanofarad, 10 to the power of 9. Okay. And then what is 1 over 5? 1 over j5. This capacitive impedance. take the magnitude of this, 1 over 5 is 0.2, right? 0.2
Yes.
ohms. That means you are shorting. You are shorting at this frequency. It's a short circuit. For short circuit and open circuit, you're going to get reflection. Because this is 50 ohms, but it is seeing open circuit or short circuit. Open circuit means impedance is infinity. Open circuit, infinity, impedance is infinity. Short circuit, impedance is literally zero, right? That's why you get reflection. Then you have the reflection coefficient formula. Do you remember? Reflection coefficient formula. Let's say if this is ZL, if Z naught, ZL minus Z naught divided by ZL plus Z naught. Let's say in this case, let's say in that case is 0.2, excuse, approximately 1. Reflection coefficient is 1. That means everything is getting reflected. If reflection coefficient is 0, then there's no reflection.
Okay, sir.
Later on, we will do some analysis. I don't know if this is the first time you're seeing this equation for calculating reflection coefficient. Did you have you learned this in electromagnetics class?
Yes, sir.
We have used this formula, sir.
Yeah, we used formula
Okay,
before.
so okay, later on we will use this again in amplifier.
Okay, sir.
All right, good question. You know, that's the way to go. Last question you learn.
Sir, can you scroll your the display to the comparison? Yes.
Yeah.
Yeah.
Uh-huh.
I want to have a look. Let's go through. Okay, thank you, sir.
So yes, a long transmission line. ZL. Okay, my drawing is a Chinchai drawing, but understand there is a long transmission line connected to a load. Then let's say you're sending a signal. So when we draw a wave like this, later on I'll go through some physics, why sometimes you draw. That's the difference between the current. When you draw like this, then it's a current, you're talking about the current. So, but when you draw a wave like this, in between, usually the waves travel in the dielectric. Waves are the one that's carrying the energy. Waves will travel at the speed of light. In the medium, maybe slightly slower, but they are the one who carry the energy. So when I draw a line like this, generally indicating that say your wave is traveling, electromagnetic wave is traveling. Okay. And then since it's a long transmission line, takes a finite time. Takes finite time. That means finite means it's not infinity or too small. It's something that's measurable. So the signal does not immediately. So because of this, it takes some time to travel. You know, it's not going to immediately reach the load. It's going to take some time. So as the signal, let's say you are the signal, and you are flying through the transmission line. So you are not going to see the load immediately because the load is very far away from the transmission line because the transmission line is very long, assuming. So the signal does not immediately see the load. Does not see the load. Therefore, the characteristics impedance relates to voltage and current produced by the electromagnetic wave, current and voltage wave. If they are always in phase, then the characteristics impedance will be constant. And this is also can be derived and show Z naught is also L over C. And what is L? L is the distributed inductance. This is the L. Remember I showed you earlier the L? The L that's responsible for charging and discharge, L and C combination. They are the one who determine the characteristics impedance. And this L and C depends kind of related to the material, the dielectric, the thickness and all that. We will look at that later also. Okay, so right now we are not really teaching electromagnetic course, but I'm just doing a quick review. As an electronics, high frequency electronics engineer, you should have some idea. Distributed inductance, distributed the distributed capacitance. Capacitor or capacitance, capacitors, inductances. Inductance or okay, capacitance. Any question so far?
So far, so good, sir.
So let's say the characteristics impedance is not something that's measurable. Note, it's not something measurable by multimeter. You cannot take your multimeter and then put across the wire and then measure it by, or just put created by the incident EM wave, electromagnetic wave. Traveling down the line. So the conductor simply guides the energy as it propagates through the dielectric medium. Okay, now let's look at a microstrip to make this concept understand clearly. Let me go and draw this microstrip. Remember last time we had a microstrip and then did we go through this? I don't know. And then you have a trace, signal trace. Okay, when the Then you have a ground plane. Then you have a signal trace, right? Signal trace, ground plane, and then you have this transverse electromagnetic wave. Because the last time, remember, we told you that some of the fields, this is a ground, there's a field, right? Some of the field is in the substrate, some of the field is in the air. Assuming this is a transverse electromagnetic wave, then you can say that all the field is constrained in the substrate. E, H, for example. So they all 90 degrees. 90 degrees to the direction of propagation. Okay, if you, let's say, if you're looking at a side view, this is your substrate. But you're looking from here in this direction so that you can see the wave propagating inside the dielectric. Assuming this is all the fields are contained in the substrate. So let me draw this SMA connectors. Semiconductor with I'm going to draw the pin in red color to show that this pin is not electrically in contact with the flange. That's a pin. And then on this side also you will have a pin. Maybe I didn't draw the pin very carefully, but it's okay for illustrative purpose. The ground plane, right? And this is the transition pin. It's a pin that's carrying the signal from the outside world and connecting it to the trace. I'm going to put the trace in red color. Maybe not trace, sorry about this. Let's put in brown. Okay, this conductor also make it brown. Okay. So when you connect this to a power supply, usually you, let's say you're connecting this to a signal generator, SIGGEN, a VG. We put usually VG. VG. And then this is a common ground. There's a current. Current traveling on the trace, reach the pin, and then it goes through a load. So I put the load in red color. Let's go through a load, ZL. Come out of the load, it's going to travel back, it's going to return on the ground plane. So it's going to return on the ground plane. And then this common ground And then it's going to return to the common ground. Common ground, common ground. These are also all the, so you guys must understand these things are all tied together. All these are common ground. You don't see them, but they are all connected together because this body is connected to the ground. This body, maybe I'm not drawing this very well. Remember, this body is also connected to the ground plane. Maybe I didn't do this very well. Okay, now mind. Okay, let's make this bigger. So all these are connected to the ground plane. So they all say potential. So it will return. Maybe ugly drawing, but it's okay. For now, that's all I can do. So the most important thing I would like you to know is if the RF is coming in this way, it's going to come out here. RF out. And this wave, the electromagnetic wave, is going to be traveling here, assuming that all the waves are contained in the substrate. Of course, there's some, remember last time I showed you here, there's some fields are leaking out. We're just assuming for now all the fields are traveling, contained in the substrate. So the wave is going to be traveling. And this is the guided wave. And who is guiding it? Who's guiding the wave? The guided wave is transferring energy. The signal trace. The signal trace and ground plane is guiding the energy. Okay, they are the one who's guiding the energy. Without the ground plane, then the signal is unguided. It will be maybe radiating as a antenna. This is not a safety ground. This is a common ground. Common ground, reference, or you can call this a reference. If this reference is not solidly connected, and then RF will behave very weird. So you know how, what's happening here? Let's say if this is not guided, you know what will happen? If this is not guided, and then the energy is traveling, if it's not guided, then it becomes an antenna. Okay. Of course, you need some length at least. If it's a dipole, it must be at least 1/2 a wavelength for it to be able to transmit efficiently. So when you design something, you have to be careful. So your grounding is very important. If this grounding is not solid, and then you will get oscillations, especially if you are working on an amplifier. You're designing for one frequency. Let's say you're designing this network analyzer or spectrum analyzer. You're designing for one frequency, and suddenly you see another signal at another different frequency. That means there's something wrong in your design. So this is oscillation, oscillating at other frequencies. Okay, maybe I will just go through a little bit more and then we continue the next time, because I thought before we go through any further, maybe what I think is I'll go through this. I've written them earlier. This is the same material that I just went through. Just to reinforce the idea, I would like to go through these notes. If you guys agree, I simply can go through these notes. The notes that I wrote by hand the last time. If you want me to go, there's a lot of writing to do. That's what I'm thinking. Okay, these are notes that I wrote last time. So, okay, we will talk about amplifier the next time. We'll talk about the amplifier next time. So I'm just reinforcing whatever we talked about so far in these notes that I wrote earlier. Can you guys go ahead and read these notes? And then next time when you have questions, you can come and ask me. Microstrip line, we already know, we talked about, right? Right or not?
Yes, sir.
So you
Yes,
already know
sir.
what is, so this dot here, this is a magnetic field or electric field? E or M?
Neutral.
E O M, E O H. H stands for magnetic. E stands H, right? Magnetic field. Magnetic field. Electric field. This is electric field. E field, electric field. Let's say if a transmission line, let's say it's a transmission line, and if you make something like this, if you make this unguided and if you make a big patch like this, what will happen? This will become an antenna. The electric field you can make the electric field go very high like this, and then they become antennas. Okay, see, this is the important, the few important things. Please try to go through this by yourself. Next time when you guys have any question, because the next time I want to move into electronics. So the dielectric, the relative dielectric is called E subscript R. But the dielectric E epsilon is relative dielectric constant multiplied by the dielectric constant of the air, where epsilon naught is this value. I'm sure most of you remember this from the physics. So usually I give you an example. RT Duroid is a trademark of Rogers Corporation, Chandler, Arizona. You have a dielectric that's available, relative dielectric constants available for 2.23, 6, or 10.5. So that the higher the dielectric constant, the less lossy the electromagnetic field lines. So we already talked about this. Electromagnetic field lines in the microstrip are not contained entirely in the substrate. This is what they mean. It's not entirely contained in the substrate. Some of them are in the substrate, but some of them are in the air. We already talked about this earlier, but I'm just pointing this out again. So therefore, this is not purely TEM mode, but a quasi-TEM. TEM stands for what again? Transverse electromagnetic wave. The quasi-TEM means part of the wave is in the air, part of them is in the substrate. In microstrip line, the phase velocity is defined by the speed of light. The speed of light divided by the effective dielectric constant. Yeah. So let's say if you're, the reason for doing that, the waves travel slower. If the outside, the wavelength I think changes, right? But inside is going to be something like that. So the wavelength changes, the velocity also changes a little bit in the medium. The c is the speed of light, ERF, EFF is the effective relative dielectric constant. EFF is related to, why they're using it, is related to effective dielectric constant, is related to relative dielectric constant, and also takes into account the effect of external EM fields. It takes into account the fringing fields in addition to the fields in the substrate. We already mentioned this earlier. Characteristics impedance of the lossless line is square root of L over C. The phase velocity is 1 over square root of LC. And the characteristics impedance of the microstrip line, if you combine these two, and then you can get this. If you solve for L in this equation and plug it in here, you will get this characteristics impedance in terms of C. So these are those things, something that we already been through earlier. Please read them. Please read them. In our dielectric, when you buy this board, right, microstrip board, then you see there's a copper thickness, and it's called T, copper thickness, very thin copper thickness. If the thickness of the copper divided by the height of the dielectric is smaller than 0.005, then you can assume the thickness is approximately 0. That means you can conclude that you can just ignore the thickness of the copper. And these are the formulas that I already pointed out earlier. If the width of the microstrip divided by the height of the dielectric, thickness of the dielectric is less than 1 or less, then you use this formula. And then you calculate the effective dielectric constant using this formula. If the width of the dielectric, the width of the trace divided by the thickness of the dielectric is 1 or more, then you can use this formula. All these are done for you automatically in the line calculator that is available in simulation software such as ADS and also in other simulation software. Do you guys have any questions so far? Any question? The next time we will discuss on how to design matching network for amplifiers, electronic amplifier at high frequencies. Guys, have any questions? Any questions?
No, sir.
Did all of you enjoy the lecture?
Yes, sir. It was good.
Are you sure?
Yes, sir.
Okay.
Minor.